Hello, everyone. Good morning, afternoon, and evening. Dear authors and invited guests, I welcome you to Technical Session 12E. My name is Amog Dhamdere, and I will be moderating this session. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome all of you to the 11th International Congress on Information and Communication Technology, ICICT 2026. The 11th edition of this conference is being held in hybrid mode. The physical event was held in London, UK, and the virtual conference is scheduled from the 25th to the 27th of February in 2026. I hope all of you will enjoy the knowledgeable and interactive sessions we have planned throughout this session. In this particular session, we will be having 6 presentations, and each presenter will be given 12 minutes for their presentation and 3 minutes for questions and answers. And on the completion of 10 minutes, I will be raising a gentle reminder. There is another request to all the participants that all of you please stay connected with us until the closing remarks are given. And just before we begin this session, I would also like to say that if you have any queries or updates, you can write it to me in the chat box. Now for the introduction of our session chairs. So our session chair for today will be Dr. Ioseb Gebelaya. I'm really sorry for any mispronunciation, sir. Okay. Dr. Josep Gabelaya is an associate professor at the Kauno Kolegija Higher Education Institute located in Kaunas, Lithuania. He is also affiliated with RISEBA University and Graceland University as well. His academic and professional expertise spans marketing, communications, management, digital learning, and leadership, with a focus on AI-driven education and sustainable practices. We welcome you to this session, sir, and I request you to give us your opening remarks.
Yeah, thank you so much for the introduction. You did a good job pronouncing my last name, so very well done. But yeah, it is the great honor and pleasure to be sessioning this chair in this session. I look on the articles. We have a really interesting topics in here, and I'm really looking forward to hear them. But from the other side, good luck to everyone presenting and sharing your knowledge and existing research. So I'm looking forward to hear more.
Thank you so much, sir. Our next session chair is Dr. Shailesh Shivaji Deore. Dr. Shailesh Shivaji Deore is an associate professor in the Department of Computer Engineering at SSVPS's Bapu Sahib Shivaji Rao Devre College of Engineering in Maharashtra, India. He has approximately 22 years of experience in teaching and academia, and he has developed strong expertise across diverse and interdisciplinary domains. His research include private cloud computing, machine learning, science as well, reflecting his focus on applying advanced computing technologies to real-world and societal challenges. We welcome you, sir, and I request you to give us your opening remarks. Oh, I'm so sorry. I was just told that Dr. Deore hasn't joined yet. So yeah, we can move on right ahead with our presentations for today. So our first presentation will be done by Estefania Silva de Cunha from the Frankfurt University of Applied Sciences in Germany. And the title of the research paper is a cross-cultural emotion recognition in human-robot interaction. Ma'am, I request you to kindly unmute yourself and start presenting.
I'll share my screen.
Sure, ma'am.
Yeah. Is it possible to see my screen?
Yes, your screen is visible and you are audible as well, so you can start presenting.
Okay, so hello, good evening or good morning to everyone. My name is Estefania, and today I will present our study on cross-cultural emotion recognition in human-robot interaction. And this work was conducted together with Eike Boderhardt at Frankfurt University of Applied Sciences in Germany. Here's a brief overview of today's presentation. I will begin with the introduction and related work, then describe the methodology, present the results, discuss the key findings, and finally conclude. In recent years, humanoid robots such as Now and Pepper have increasingly been used in healthcare, education, and service environments. And for these interactions to feel natural and empathetic, facial emotion recognition plays a central role. However, most existing systems rely on relatively homogeneous Western-centered data sets, and this raises concerns about bias, cultural generalization, and inclusiveness, especially for underrepresented population. And in this study, we evaluate how reliability now robot recognizes emotions across different cultural groups and facial conditions, and whether an external model can improve performance. Yeah. Previous work on emotion recognition in humanoid robots mainly relies on facial expressions captured by onboard cameras, sometimes combined with additional cues such as pitch, tone, or physiological signals. In practice, these approaches are typically implemented and tested on humanoid robots platforms such as Now and Pepper, and are often evaluated under controlled laboratory conditions, for example, using frontal faces, stable lighting, and exposed and posed expressions. Although recent deep learning and multimodal approaches have improved overall recognition accuracy, important limitations still remain. Many studies still rely on predominantly Western data sets. Performance tends to decrease for negative emotions such as fear and disgust, and cultural diversity as well as facial anomalies remain largely underexplored. And because these systems are designed to function in real world, to be used with diverse users, robustness and inclusiveness are essential. And these limitations directly motivate the present study. The goal of this study was to compare Now's built-in emotion recognition system with an external pre-trained model under identical conditions. And for this purpose, we evaluated a data set of 560 facial images representing 8 world regions, including Europe, South and Southeast Asia, North and Sub-Sahara Africa, the Middle East, Latin America, and East Asia. The dataset covers 5 groups, from 5 age groups, from children to elderly individuals, 2 genders, and 7 basic emotions. And those are happiness, sadness, anger, surprise, disgust, fear, and neutral. 2 recognition approaches were tested. The first approach used Now's onboard emotion recognition within the Now key environment, and this system operates directly on the robot and supports 5 emotion classes, but it does not recognize all of the emotions that I just mentioned, fear and disgust. And the second approach processed the same images off board using highlight feature detection and combined with deep face. And this external pipeline supports all 7 emotion classes. And due to the limited availability of suitable public data sets for specific demographic combinations, part of the data set was augmented using AI-generated images. And in addition, 80 images depict individuals with facial anomalies, and both systems were evaluated on the same exact data set to ensure a fair and consistent comparison. This slide shows a visual overview of our data set, and as it can be seen, it includes a wide range of ages, from children to elderly individuals, as well as different genders and regional backgrounds. I'll now move on to the results, starting with the overall classification and accuracy for all emotions in both systems. What stands out immediately is that both systems perform best on happiness with an accuracy of 88.5%. This was the most reliably detected emotion for all to build for both the built-in Now emotion engine as well as the external model. In contrast, performance dropped sharply for negative emotions. For fear and disgust, the built-in Now system achieved 0% accuracy, meaning it was not able to recognize these emotions at all. The external deep face and highlight features approach performed better, but disgust remained the weakest emotion with an accuracy of 23.4%. And overall, this shows that Now performs really good for positive emotions, while the external model improves recognition of more complex negative emotions. Now breaking the results down by region. reveals noticeable variation in performance. What stands out is that both systems achieved their best performance in the Middle East, where emotion were recognized consistently well across emotion classes. Notably, the external approach was even able to recognize the more difficult emotions, such as fear and disgust, with relatively high accuracy in this region, something that the built-in now system was not able to achieve at all. And in contrast, performance in South Asia was really low, and both systems struggled across most emotions category, with happiness being the only emotion that remained relatively stable. There were also additional findings related to gender, age, and facial anomalies. For gender, the largest recognition gap appeared in East Asia, where both systems showed clear differences in performance between male and female faces. However, this imbalance was largely reduced by the deep face and highlight features model, which showed more balanced performance. And looking at age groups, both systems performed best for young and middle-aged adults, while recognition accuracy dropped noticeably for elderly individuals. And as for facial anomalies had a strong negative impact on performance. Out of the 80 images representing facial anomalies, the built-in now emotion engine correctly recognized 39, while the deep face and highlight features model recognized 41. Although the external model performed slightly better, both systems struggled, highlighting a very important limitation. And here we see the confusion matrices of both systems. On the left is Now's built-in emotion engine, and on the right, the external deep face and highlight features model. The diagonal side shows correct classifications, while the off-diagonal values indicates misclassifications. For now, it is immediately clear that fear and disgust are completely misclassified, as these emotions are not supported. For example, fear, for example, is often confused with surprise, and disgust is often mistaken with anger. And this aligns really well with prior research showing that subtle or low intensity emotions are especially difficult to detect. And the external model shows a similar pattern, but with broader coverage. Happiness is recognized very reliably, while sadness is often confused with neutral. And the external system recognizes fear and disgust, unlike now, but still some misclassifications still persist. After analyzing the results, we can see that our findings are largely consistent with previous research. Regions that are typically underrepresented in training data, such as South and East Asia and Sub-Saharan Africa, show lower recognition accuracy, while Europe, Latin America, and the Middle East perform more reliably. We also observe a clear emotion-dependent pattern. Happiness is the most robust emotion across both systems, whereas fear and disgust are consistently the most error-prone. And this is just that subtle and cultural variable expressions remain challenging for automated recognition systems. At the same time, our study has also some limitations. These include the overall data size, the limited number of facial anomaly cases, and the restricted computational capacity of the onboard now system. To conclude, our results show that both systems have strengths, but neither clearly outperforms the other in all scenarios. Challenges remain, especially for negative emotions and facial anomalies. And rather than replacing one system with another, a combination of onboard processing and advanced deep learning methods may offer a more robust solution. Ultimately, improving emotion recognition in human-robot interaction will require more inclusive data and culturally aware system design. That's it for the presentation, and thank you so much for the attention.
Thank you for your presentation, ma'am. Dr. Gebelaya, do you have any questions for our speaker?
Really good work here. I really like the comparative data here, what we are showing. My quick question would be, based on the experiment that we had, does the interaction effect between region, age, gender produce some kind of compounded bias patterns?
I don't know
If you
if I
have,
understand correctly your question.
yeah,
Do
I
you
would say, sorry.
can you maybe explain it again?
Yeah, I was wondering if there is some kind of the bias between region, age, and gender based on these experiments with Nayo and then.
We actually did notice some bias, specifically with images from participants from the Middle East. But the most interesting part is that tools were the images that were relatively more generated with AI. So tools, this is something that also should be generated, but it's an indicator that there is some bias.
No, that's good one because usually in the marketing we talk about the consumer behavior patterns and then we talk about this gender, age, and then region categories and how does it process. So thank you so much for your work, really great work, and hopefully we will see more of your work in the future as well.
Thank you.
Just before we move ahead, our session chair has joined us. Give me just a second. Yes, so our second session chair for this session is Dr. Shailesh Shivaji Devre. Dr. Shailesh Shivaji Devre is an associate professor in the Department of Computer Science at SSBPS's Bapu Sahib Shivaji Rao Devre College of Engineering in India. And he has approximately 22 years of experience in teaching and academia. And he has developed a strong expertise across diverse and interdisciplinary domains. And his research interests include private cloud computing, machine learning, IoT, network security, and biomedical science, reflecting his focus on applying advanced computing technologies to real world and societal challenges. We welcome you, sir, and I request you to give your opening remarks as well as any questions if you might have for our speaker.
Hello.
Hello,
Hello.
sir.
Shall I hear, sir? Hello.
Yes, sir, you are audible.
Yeah, yeah. Okay, sir. Now session is start, na, sir?
Yes.
Okay, okay. So, number of participants, that please, what the time is given, that is your presentation is must be wind up in that particular time. Okay. And there is a who is the first, sir? Shall I? Means we know that who is the first researcher or presenter?
So we are actually done with our first presentation for today. I am
Yeah,
not
yeah.
sure if you were present,
Okay.
but yeah,
So continue, sir. Okay, sir.
yes,
Hello.
thank you so much.
Yes, yes, yes.
We can now move on to our next presentation for this session, which will be done by TDBS Ruberu. I am really sorry if there are any mispronunciations, but she belongs to the Open University of Sri Lanka from Sri Lanka. And the title of the research paper is Enhancing Automated Testing in Low Code / No Code Development Using Cognitive Complexity Aware Quality Assurance Frameworks. So, ma'am, I request you to kindly unmute yourself and start presenting.
Am I audible?
Yes, ma'am, you are audible.
Yeah, I will share my screen. Right. I hope you can see my screen now.
Yes, ma'am, your screen is visible and you are audible as well, so you can start presenting.
Yeah, right. Yeah. A pleasant day to all of you. I'm TDPS Ruberu, and I'm from Faculty of Natural Sciences, the Open University of Sri Lanka. And my research topic is enhancing automated testing in the low-code, no-code development using the cognitive complexity-aware quality assurance framework. Then we move to the next slide. Yeah. Here's a quick overview of what we'll cover today. Then we move to the introduction. Low-code, no-code platforms have transformed the way software is built. They are accelerate delivery through the visual models, configuration-driven logic, and reusable components, enabling non-traditional programmers to build a functional system without deep engineering expertise. However, some challenges occur for quality assurance. The same abstraction layer that simplify development also of underlying control flow on inheritance relationships and execution logic. As a result, automated testing suites in low-code, no-code environment are often brittle, hard to maintain, and poorly aligned with the actual complexity embedded within the platform-generated artifacts. Testing becomes a reactive, identifying failures only after deployment rather than preventing them. And at the heart of this problem is something that is largely invisible cognitive complexity here. What is cognitive complexity? Cognitive complexity is simply the mental effort required to understand, modify, and reason about software behaviors. Unlike structural metrics such as complexity, which count control flow paths, cognitive complexity models, the human comparison burden, such as factor in the nested depth, conditional branching, and control flow chain and inheritance hierarchies. These are the what is the cognitive complexity. Then we move to the related work. The research landscape has three main traits. First one is the classical complexity matrices give us a structural and size-based measurements, but this fails to capture the comparison difficulties. The second one is the cognitive and composite matrix addresses some gaps, like the weighted composite C being measured by the integrated nesting and the control flow of the single model. The third one is automated tools such as ICICT have demonstrated that those cognitive metrics can be computed, monitoring continuously, and integrated with the development workflows. These are the identified related works. Then we come to the research gap. As shown here, the gap is clear. We have validated cognitive complexity metrics, we have measured automated quality analysis tools, and also we have documented the quality assurance challenges in the no-code development. But there is no systematic bridge connecting this. There is no guidance on how cognitive complexity awareness should inform the test prioritization and regression planning or long-term maintenance strategy in the highly abstracted environment. Then we come to the methodology part. The research approach is conceptual and the framework driven. Rather than proposing the new complexity metrics or the running large-scale experiments, I synthesize valid cognitive complexity principles with the automated testing practice. And the resulting framework has four logical stages. First one is artifact identification. Second one is a complexity characterization, automated quality assessment, testing strategy alignment. This is the overall conceptual framework I propose. I will explain it in the next slide. The first one is the artifact identification. It's mean treating low-code, no-code workflow rules, triggers, and complexity barriering entities. The second one is a complexity characterization. In this stage, we mapping the cognitive principles onto the observable properties like nesting depth and branchings. Then third one is automated quality assessment. In this stage, we continuously monitoring of the complexity related risk. The last stage is the automated testing strategy alignment. using the complexity insight to inform the test prioritization, regression, scope, and maintenance planning. This is the overall idea about the proposed conceptual framework. Then we move to the next slide. In the discussion, let me highlight the key implications of this work. The first one and the most important one is the abstraction does not eliminate complexity. It's redistributed it. And what was visible in the scope source code on now live in the visual workflows and the rule configuration invisible for the testers. This is why convolutional UI and functional testing is fundamental insufficient. It missing the cognitive load embedded in the logical structure entirely, leading to the reactive defect detection. The second major implication is around the maintainability. The third one is the limitations of the existing metrics like uniform weighting, composite conditionals, and not blockers. They are motivation for the context-aware adoption. The final one is a platform dependent design of the framework means it can be applied across the diverse low-code, no-code ecosystems. I will move to the limitations of my paper. I want to be transparent about the limitations because acknowledging them actually strengthens the contribution and map the road ahead. So the most significant limitation is the framework is conceptual. Has not yet been validate or real platform. It is also inherit the non-weaknesses of the existing cognitive complexity matrices. Then we propose the conceptual framework. And also platform diversity is not fully addressed here. Then we come to the conclusion. In conclusion, low-code, no-code abstraction does not simplify the complexity. It hides it. Convolutional functional testing is not enough to manage the complexity-driven quality risk in the environment, and cognitive and composite complexity matrices provide the right lens for the guiding testing decisions. Then as a solution, we propose the four-stage framework: artifact identification, characterization, automated assessments, and strategy alignment. This framework provides a structured, theoretically ground path from the reactive validation to the proactive quality management, and it is does so in way for the result. Then we come to the future work. We have four directions for the future work. First one is a validation part, testing the framework on real low-code platform and measuring in its impact on defect rates, maintenance effort, and regression stability. Second one is a platform-specific adaptation for the platforms like Power Apps and Mendes. Third one is a AI and machine learning integration using the historical complexity data to predict the automated prioritization recommendation. The fourth one is an end-to-end DevOps toolchain integration. These are my references used to create the research paper. Then we come to the end of my presentation. Thank you very much for the attention and the time.
Thank you for your presentation, ma'am. I now ask our session chairs if they have any questions for you.
Yeah, I can go ahead. Good work on your research work. My quick question will be, based on your conclusions on your work, how does cognitive complexity within low-code, no-code workflows impact effectiveness and maintainability of this testing for in this environment?
Yes. In this cognitive complexity, we measure the human effort. We need to understand the hidden complexity of the source code. Then we most important thing is tester we need to test. We have get some idea about the all part of the source code. Then we get some computer complexity matrices and measure the hidden complexity between the source code. Then we can do the testing part effectively. Yes.
All right, thank you very much. Keep working.
Yeah, thank you very much.
Dr. Deore, do you have any questions for our speaker?
What are real type applications? Hello.
Yes, sir, you're audible. You can ask your question.
What are real type applications of your research work?
Sorry.
He
Real
means to
time
ask what are your
applications.
real-time applications for your research?
Yeah, this is a conceptual framework. We are not currently use it, but we can apply it for the current usable applications like power. We can use this concept for the current existing applications. And we are not validated. It's a conceptual framework only currently. We will develop it further in the future enhancements.
Okay. Do you compare your work with existing methods?
Sorry?
He's asking if you have
Existing
compared your research work with any existing methods.
Yeah. Currently existing methods, we use Power Apps and other enterprise applications. We compare it and we do some literature review of the existing systems and identify they are not considering the complexity matrices. Then I identify it and give some literature survey here.
Okay, fine.
Well, thank you so much for your presentation, ma'am.
Yeah, thank you very much.
Yes, we now move on to our next presentation for this session, which will be done by Murphy Bonkogia Lomboli from the University of Johannesburg in South Africa. And the title of the research paper is Forecasting Rainfall and Demand for Ekurhuleni leak-safe models with SAW/TOPSIS decision support. So yeah, sir, I request you to kindly unmute yourself and start presenting.
Okay. Hello, can you hear me?
Yes, sir, you are audible.
Okay. Please let me know once you're able to see my screen.
It's still loading, sir.
Okay.
Yes, your screen is visible and you are audible as well, so you can start presenting.
Okay. I'll start now. Good morning, good afternoon. My name is Murphy Lomboli. I'm a research student from the University of Johannesburg and here to present our study, which is titled Forecasting Rainfall and Demand for Ekurhuleni Leak-Safe Models with SAW and TOPSIS Decision Support. So a quick motivation behind the study is this. In urban water systems, a forecast is only helpful if it is credible and if it can be turned into a decision. That is why our work is built around two ideas, the first of which being leak-safe forecasting and the transparent ranking layer using SAW and TOPSIS to choose operational models. Three of the main objectives in carrying out this study, the first of which is to build the leak-safe monthly models for rainfall and demand using past-only features, strict train and test split, and honest baselines for the municipality in terms of rainfall and the potable demand. And the second objective is to produce compact diagnostics and a 36-month outlook using lagged features and residual checks. And then the third objective is to link model skills to ranked policy actions again with soil and topsies, based on parameters such as RMSE, MAE, MAPE, and R squared. To provide a little bit of context, the city of Ekurhuleni is a large metro of nearly 2,000 square kilometers with a population of approximately 4 million people. It relies heavily on Rand-Water's Vaal River supply chain system, and because of this, it makes reliability planning a real operational challenge. On the more technical side, our feature engineering included the usage of legs, month means and sums, as well as monthly seasonality over the period of between 2011 to 2025. For evaluation, we trained the model on the 2011 to 2022 dataset, and then we tested the model using the dataset from 2023 to 2025 by making the model predict the data within the testing period, and thereafter comparing the results against baselines such as persistence, seasonal naive, and climatology. For the 36-month outlook, we forecasted recursively and showed practical uncertainty bands using the parameters mentioned earlier, like RMSE, R squared, and the likes. We trained and tested several machine learning models. And what we found is that for rainfall, the model that performed best is bag trees. It captured the December to February peaks and the June to August minima quite well. And then we got an RMSE value of 9.1 with the R squared value of 0.96 against the baselines. And then for the demand model, the model which performed best was Metin 502 GPR, as it was able to track smooth demand with the RMSE value of 17.1 megaliters per day, an MAP value of 1.4, and an R squared value of 0.76. We use these models to make 36 months forecast. And then in terms of the rainfall, we forecasted summer wet and winter dry cycles quite well. And then with an appropriate 995 to 1,025 megaliters per day in terms of the demand band, with small month-to-month ripples. As an additional layer to support operational decision making, we took a further step in employing multi-criteria decision making, and the result of which both soil and topsies independently selected Metin 5/2 GPR with a near 1-for-1 agreement on the ranking. So the plots that you're looking at here are the results from the testing that we did. As I mentioned earlier, that the testing was conducted from the period of 2023 to 2025. So the first plot on your left compares the actual monthly rainfall against what the model had predicted over the testing period. And as you can see, it also includes the baselines, which I mentioned earlier, the persistence and the seasonal naive against the prediction from the model. The key observation that we can make here is that when the observed rainfall rises into the wet season and drops into the dry season, the model generally follows the same up and down seasonal rhythm. There are some under predictions of the most extremes, but generally the model has learned the demand season, the rainfall season better than the baselines. The scatter plots that you're seeing on your right shows how close the model's predictions are to the true rainfall values. Each dot there represents a month of the year, and the diagonal line represents the perfect prediction. So essentially here, the closer the dots are to the line, the more accurate the predictions are. And as shown there, the model has a strong overall relationship. The analogy in terms of the water demand data is still the same. We're still comparing the actual water consumption in megaliters per day to the model's prediction. The model tracks the overall level of demand and follows the general trend. The difference mainly here is that the predicted line is a little bit smoother than the actual line. So which can be a sign of underprediction on sharp peaks and an overprediction on sudden drops. But in terms of planning, this is often acceptable because it gives a stable prediction expectation of the water consumption. The same thing with the demand. We've also provided an analysis in terms of the perfect prediction. And as you can see there on the diagram, the dots for each month are relatively close to the perfect line, which is a show of the accuracy of our work. So as I mentioned a little bit earlier, that as a further step, we did employ multi-criteria decision systems. And from the graph that you're seeing in front of you, both SOAR and TOPSIS are, as I mentioned, a part of multi-criteria decision techniques. You'd usually use these when you have a lot of criteria to consider when making critical decision. Basically, SOAR works by assigning additive weighting, whereas TOPSIS works by similarity to the ideal solution. In this plot, essentially, the higher the scores, the better. And we applied this as a further reinforcement to the selection of the best model to use for water consumption. From the analysis that we have done, Meton GPR 5/2 is again chosen as the best model for demand forecasting. From the model training and the testing, we made a 36-month forecast for both rainfall and water demand. Before I continue, let me just reiterate that in this analysis, we did take both factors as univariate. So to continue in
Excuse
terms
me, sir.
Mm,
I just wanted to remind you that you are left with 2 minutes of presentation time.
okay, thank you.
Yeah, thank you, sir.
Okay. In terms of the rainfall, the forecast matches mostly driven by the seasonal structure, and then in terms of the demand, the variations are small, suggesting that we should expect a stable water demand over the next 3 years. So from our study, we made 3 conclusions. The first of which, leak-safe models beat the naive baselines. And then the second conclusion we made is that the Merton 5/2 is a robust operational forecaster. And then the third conclusion we make is that the framework supports non-revenue water reduction and reliability. I would also like to acknowledge people that have made contributions to this work, which includes various departments here and my supervisors. Thank you.
Thank you so much for your presentation, sir. I now ask our session chairs if they have any questions for you.
Hello.
Yes, sir, you can go ahead.
Yes. How you motivated to do this research work? This is a general
Sorry?
type question. How you motivated to do this kind of research work or type of research work?
So, as I mentioned earlier, is that instead of just focusing on the theoretical aspect of the study, we took it a little bit further by providing some sort of practical guidelines of what could be looked at operationally for the next 3 years. So that's the fundamental motivation behind the study is that we want to provide an operational guideline for the next 3 years.
Okay. What are the different challenges that you face at that time when you write this paper or do this research work? What are the challenges that you face?
Oh, okay. So in terms of challenges, the first of which was data acquisition. That was a little bit of a challenge because initially we wanted to include demographic details like population growth into the study, but then uh, the data here is published at a certain interval. So as of now, there isn't enough data pool to actually incorporate those. So that's why I mentioned that in the study, we took both factors as univariate. So that's one of the challenges that we had was data acquisition.
Okay. Is this model is applied a real world application or to solve the real world problems?
Yes,
Yes or
as I
not? Only
mentioned,
give yes or no.
yes, it is. As I mentioned, in terms of providing practical operational future outlook.
Okay. Yes. Fine.
Dr. Gabalaya, any questions?
No questions from me. Good work.
Well, thank you for your presentation, sir. We can move on to our next speaker for this session. So our
Thank
next speaker is Jose Manuel Meza Gonzalez from the Metropolitan Polytechnic University of Hidalgo in Mexico. And the title of the research paper is Gridistil, a systematic approach to bridging the capacity gap in clinical image classification. Sir, I request you to kindly unmute yourself and start presenting.
Okay, thank you. Can you hear me?
Yes, sir, you are audible.
Thank you. Let me share my screen. Mhm. Can you see my screen? No?
Yes, your screen is visible. And just a small request, it would be great if all the presenters would have their cameras on as well, but it's absolutely fine if they aren't.
Okay, let me start. Well, hello everyone. Thank you for this space. As a part of the master degree of the Metropolitan University of Hidalgo, we conclude this a presentation. The grid is still a systematic approach to bringing the capacity gap in clinical image classification. This is our agenda that we talk about this topic. To start with this is essential to understand the motivation behind our research. While integrated deep learning into medical diagnostics offers immense potential, it faces a critical hurdle, the high computational demands of the state-of-the-art models. These high-capacity models often require processing power and memory that far exceed the resources typically available in real clinical settings, or for example, in many hospitals or health centers, particularly in resource-constrained environments. Access to high-end GPUs or supercomputer clusters to run such complex network is simply not feasible. This technological debate creates a significant deployment gap. Powerful models are currently too heavy to operate efficiently on portable medical devices or local systems to rapid consultation. Consequently, there is a well-documented need lightweight models that preserve diagnostic accuracy while remaining efficient enough to function without the overhead of general purpose networks. The exact challenge that we need to develop, we call the grid distill. The goal is to provide a solution to create small models that provide a good accuracy, and that we can implement in small devices or with small air requirements. To ground our research is essential to review the key milestones that define the current state of the model compression. First, we must look at the work of Hinton, who formalized the knowledge distillation. That is a technique that we use. They introduced the groundbreaking concept to using soft targets to transfer what is known as a dark knowledge for complex teacher or for complex neural networks to a small neural or students, allowing the reader to learn more than use the final labels. However, as modern architectures, Mizarde identified a significant hurdle known as the capacity gap. They discovered that if the architectural difference between the teacher and the student is too vast, the student fails to cover optimal. This is a central challenge that our work, Grid Distill, especially aims to address. And also, we base our research about a survey of knowledge distillation that we use response-based distillation between the teacher and the student configuration. Now, I want to like to guide you through the grid distill framework, which represents the core of our methodology as illustrated in this diagram. The first step is to get the data acquisition. We use the MetMNIST B2 benchmark, especially selecting for diverse clinical domains, pneumonia, breast, retina, and derma, to ensure our framework robustness across the different medical modalities. All-image, we standardize to 28 by 28 resolution to maintain a low computational footprint. Next, we establish a hierarchical teacher-student configuration. We employ a high capacity teacher model. In this case, we use a convolutional neural network with approximately 20 million parameters. And also for the student, we use a convolutional model little that achieves a remarkable 99% reduction in parameter count compared with the teacher. The main part of our approach is the knowledge distillation framework. Here, the student model doesn't just learn from the hard labels of the ground truth. It also learns from the soft labels generated by the teacher. This is managed with a combined loss function with balance the standard cross entropy with a callback divergence of the teacher knowledge. To ensure this transfer is optimal, we introduce the grid distill strategy. Instead of relying on arbitrary selection, we perform a systematic grid search to fine-tune two critical hyperparameters: temperature, which controls the smoothness of probability distribution, and alpha, which regulates the weight of the teacher guidance. Finally, the rigorous optimization leads our goal of optimize a compact model. Also, to check or to test this framework, we have to compare the AUC and accuracy to bring the capacity back and make it truly viable to resource-constrained clinical environments. Having established our framework, I will now focus on the technical concerns of our research grid distill. In many existing studies, hyperparameters for knowledge distillation are often chosen through heuristic or even arbitrary selection. However, in our introduction, parameters optimized for general computer vision frequently fail. To address this, we propose the grid distill, a systematic research strategy designed to ensure optimal knowledge transfer. We focus on two critical variables: the temperature, as I mentioned, is modeled the probability distribution, and the distillation weight, which we explore between 0.1 and 0.9. This hyperparameter is crucial because it regulates the balance of the guidance. And finally, our objective is to maximize the AUC and the accuracy simultaneously to ensure the coverage, the speed in maxi capacity reduction. To establish our baseline, before we need to train all models, the teacher and the student from scratch using a systematic research. The proposed to train before is first to get the optimal teacher or the best teacher to transfer to the students, and the student is also to compare the transfer of the knowledge transfer and compare what is the difference between them. In this case, when largest teacher model generally set the performance ceiling, our compact student models provide remarkably efficient. And a standout result was the pneumonia MNIs, where the students of convolutional actually surpassed the teacher accuracy. This confirms that even before distillation, these compact architectures are highly capable of capturing fundamental diagnostic features, providing that the size doesn't always dictate clinical reliability. Well, the experimental result demonstrates that knowledge distillation is a highly effective strategy, in this case for clinical image classification across all evaluated datasets. Distilled students consistently outperform those training from scratch, showing significant gains in both accuracy and AUC. A phenomenon of major critical relevance is observed when constrain our models against STEM-heavy architectures. In conclusion, our study successfully demonstrates that our proposed grid distill is a robust strategy to bring the capacity gap in a medical environments by implementing a systematic hyperparameter optimization. We achieve almost of 19% reduction in the parameter count with convolutional networks. The evidence is clear. Distilled students consistently perform those training from scratch. In this case, the distilled models get major capacity to classify versus the students that we train from the scratch. And the future, for the future work, we have a plan to explore the multi-level assistant distillation for more complex 3D medical imaging tasks. Also, we will investigate the feature-based distillation to refine the knowledge transfer. And finally, we have the plan to implement this framework to real-world deployments on H8 devices in order to confirm that all of them are working as expected. Thank you so much. I don't know if you have question about this project.
Thank you for your presentation, sir. I now ask our session chairs if they have any questions.
Yeah, I'll go ahead and ask a first question. Really interesting work here, and I like the comparison between teacher and student. My question will be based on your research work. How does response-based online knowledge distillation improve the performance of compact student models compared to the training them from scratch?
Yeah, as we see in the results, using this grid distill, we can transfer from the teacher, and we cover all options as we know the grid distill capacity in order to select the best result about this combination or hyperparameters.
Good. Thank you. Really good work. Good luck.
Thank you.
Dr. Deore, do you have any questions for our speaker? Dr. Deore, am I audible to you? Hello,
No
sir,
more
am I audible?
questions, sir. Yes, yes.
Oh,
No
okay,
more
okay.
questions. Please continue.
Okay, thank you so much, sir. Thank you for your presentation, sir. We will now be moving on ahead to our next presentation for today. So our next presentation will be done by Meryem Zoglami from the University of Tunis El Manar in Tunisia. And the title of the research paper is Participation in Virtual Dermatology Care Communities and Intention to Consult a Dermatologist, a Mediating Role of Patient Empowerment. Ma'am, I request you to kindly unmute yourself and start presenting.
Hi, hi everyone. I will share my. One second. Sorry.
Sure, ma'am.
Sorry. Good for you? It's okay?
Yes, ma'am, your screen is visible and you are audible as well, so you can start.
Okay, thank you. Good morning, everyone. I'm Meryem Zoglami. I'm a researcher and lecturer at the University of Tunis El Manar, and I am thrilled to present our recent research today. Our paper is titled Participation in Virtual Dermatology Care Communities and Intention to Consult a Dermatologist, the Mediating Role of Patient Empowerment. During this presentation, we will explore what happens with when patients with skin condition turn to the internet for help, and how those online interactions ultimately affect their real-world medical decision. To set the context, let's look at the rapid rise of virtual health communities, or VHCs. With the explosive growth of digital technologies, patients are no longer passive reception of medical care. They are actively going online to find answers. VHCs have become central arenas where people exchange not just medical facts, but experiential knowledge and profound emotional support. This phenomenon is particularly striking in the field of dermatology. Skin conditions are highly visible. They don't just affect physical health, they heavily impact a person's body image, self-esteem, and social interaction. Because of this social sensitivity, patients often seek refuge in online peer groups. But this raises a critical question for health care systems. Does this online peer support actually foster a readiness to consult a medical profession, or does it encourage self-diagnostic, leading patients to delay vital clinical care? That exact question brings us to our to our research gap. In the existence literature, there is a clear tension in care-seeking behaviors. Prior studies extensively document that patients gain psychosocial benefits from these platforms. However, the evidence regarding how this impacts formal healthcare engagement remains highly fragmented and equivocal. Some studies suggest online groups make patients proactive, while others warn they might replace the doctor entirely. Furthermore, existing research has heavily focused on end-state outcomes like user satisfaction or general well-being. What has been missing is an understanding of underlying mechanism. Our study addressed this gap by introducing patient empowerment as the crucial mediating variable. We wanted to see exactly how the support gained online translates into the specific intention to book an appointment with a dermatologist. To build our model, we anchored our research on 3 theoretical pillars. First is social support. In virtual communities, this comes into distinct flavors. Information support, which is the sharing of advice, treatment, and factual knowledge, and emotional support, which provides empathy, reassurance, and a sense of belonging. The second pillar is patient empowerment. We defined this not a medical outcome, but as a psychological state. It is the perceived capacity of a patient to comprehend their condition, make informed choices, and shift away from a traditional paternalistic model of medicine to become an active partner in their care. Our final pillar is the consultation intention. We argue that a truly empowered patient doesn't avoid doctors. Rather, they recognize the limits of self-management and know exactly when specialist intervention is necessary. Based on this concept, we formulate 5 main hypotheses. H1 and H2 propose that active participation in virtual dermatology communities positively increases both perceived information and emotional support. H3 and H4 test the impact of these supports on patient empowerment. We hypothesize that both information and emotional support would make a patient feel more empowered. H5 posits that this resulting patient empowerment will directly and positively influence the intention to consult a dermatologist. Finally, we proposed an overarching mediating effect that empowerment act as the essential bridge connecting online participation to offline clinical visits. To test our theoretical model, we adopted a quantitative cross-sectional design. We distributed an online survey specifically targeting individuals who were active in virtual dermatology communities, primarily through Facebook forums and specialized social media support groups. We collected a robust sample of 229 valid responses from members who had participated in this community with the past 3 months. All our theoretical constructs were measured using established validated 5-point Likert scales. For our data analysis, we utilized partial least squares structural equation model, or PLS-CM, which allowed us to simultaneously evaluate our measurement and structural models alongside the bootstrapping to strictly test our mediation effect. Let's move on to our findings, starting with the measurement model. As you can see in the table, the psychometric properties of our constructs were highly satisfactory. The internal consistency of our scales was strong, with the Cronbach alpha and composite reliability scores well above the standards 0.70 threshold across the board. Furthermore, the average variance extracted value generally exceeded the 0.50 benchmark, confirming convergence. It's okay?
Yes, ma'am, your voice is audible. You can continue.
Okay, sorry. We also established discriminant validity. In short, our measurement instrument was reliable and valid, providing a solid foundation for testing our structural paths. Now, for the most interesting part, the structural model. First, our baseline hypotheses were strongly supported. Participation in this virtual community highly drives both emotional support and informational support. People are clearly getting what they come for. We also found strong support for H5 empowerment drives the intention to consult empowerment directly and positively drives the intention to consult a dermatologist. However, the pathways leading the empowerment yielded a surprising and critical finding. As expected, emotional support significantly fostered patient empowerment, but contrary to our expectation, informational support did not significantly increase empowerment. Why is this? In the context of, we think, in the context of dermatology, where symptoms can be visually alarming and highly varied, an abundance of peer-generated information often leads to information overload. Conflicting advice about creams, diets, or triggers might actually confuse the patient rather than empower them. It is the empathy and the reassurance, the emotional support that truly gives them the confidence to take charge of their health. This leads us directly to our mediation effect analysis. We confirmed a significant indirect effect of 0.372. This statistically confirms the patient empowerment acts as a crucial bridge. Participation in this online platform doesn't just automatically send people to the doctor's office. Rather, the participation provides emotional reassurance, which in turn builds the patient's internal confidence and empowerment. It is this newly acquired empowerment that serves as the principal catalyst, converting online peer engagement into proactive offline help-seeking behavior. So, what are the
Excuse me,
implications?
ma'am.
Yes.
Just a reminder, you have 2 minutes of presentation time left.
Okay, thank you. What are the implications of our funding for platform managers and moderators? The message is clear. Virtual community should not just be managed as cold repositories of medical facts. To truly help users, moderators must foster a culture of empathy, actively encouraging effective and supportive interactions. For clinicians and dermatologists, our study offers reassurance Online communities are not your competitors. They are complementary tools. They reduce patient anxiety and build self-efficacy. An empowered patient entering your clinic is a better partner in their own treatment plan. Theoretically, our research refines the concept of empowerment in chronic care. It's highlight that in visually and socially sensitive field like dermatology, empowerment is heavily reliant on psychosocial resources, feeling understood and less alone, rather than just the accumulation of factual medical data. To conclude, virtual dermatology communities do not replace formal medical care. Instead, when they successfully provide emotional support, they empower patients to step out of the shadows and confidently seek the professional help they need. Thank you so much for your time and your attention for this presentation. And I would now delight to answer any question you may have.
Thank you for your presentation, ma'am. Dr. Gabalaya, do you have any questions?
Really interesting research work, but no questions from my side at this moment.
Okay, thank you, sir. Dr. Devre, do you have any questions for our speaker? Dr. Devre, am I audible? Hello, sir. Am I audible?
Hello.
Yes, sir. I was asking you if you had any questions for our speaker.
No, sir.
Okay, thank you so much, sir. Well, we can now move on to our next presentation for the next presenter for this session. Our next presentation will be done by Hector Rafael Morano Ocuno from the School of Engineering and Science in Mexico. And the title of the research paper is Prompt Engineering for the Kinematics Analysis of Mechanisms. Sir, I request you to kindly unmute yourself and start presenting.
Okay, perfect. Yes, okay. Okay, hello everyone. I'm Hector Morano. I work for Tecnológico de Monterrey, campus state of Mexico. The title of this presentation is Prompt Engineering for the Kinematics Analysis of Mechanisms. So this is the agenda I'm going to follow. First, I will give a brief introduction. Then I will describe the objectives of this work. Subsequently, I will mention the methodology that we use. And finally, I will share the conclusions and future work. So generally, when AI is used to solve problems, it is associated with computer engineering. However, users can find AI applied to diverse areas of knowledge. This work aims to introduce mechanical engineers to the use of prompt engineering to perform kinematics analysis of mechanisms. So having users compare the result with those obtained by the AI allows them to verify their calculations. So the objectives of this work were to introduce mechanical engineers to the use of AI in their disciplinary area. The second one was to explore the results of kinematics analysis generated by LLMs. And the third one was to determine the scope of LLMs to performing kinematics analysis of mechanisms. Here we have the computational resources. So we use for the LLM ChatGPT, base GPT 5.2 in its open source version. The computers employed were laptops and with an i7 processor with 2.5 gigahertz and 32 gigabytes of RAM. The computer program to perform mathematical operations for the kinematics analysis was MATLAB. So the methodology consisted of the sequence of steps used to conduct the research. We can see it in figure 1. Initially, ChatGPT was asked to identify the provided image, which represent the case study. The case study is shown in figure 2. So subsequently, the variables required to calculate mechanisms inverse kinematics were provided, and ChatGPT was asked to identify any possible ambiguities. So in figure 3, we can see the prompt that we use. Due to the identified ambiguities, it was not necessary to modify the mechanism diagrams. Only the prompt in figure 4 was generated to clarify the missing information. And ChatGPT was asked to identify the mechanism degree of freedom using Kurzbach criterion. Finally, ChatGPT was asked to calculate the angles, angular velocity, and also angular acceleration of the different links for the different theta angles. And when ChatGPT was asked to identify the mechanism's image, it had no problem describing it. It was able to distinguish the different links, their angles, and also some angular velocity. ChatGPT also identified the ambiguities that we can see in table 2. Using a prompt to clarify the ambiguities, ChatGPT rechecked them and provide the response shown in figure 7. So ChatGPT had no problem applying Kurzbach criterion and calculating the mechanism degree of freedom. Also, ChatGPT response is shown in figure 8. So the degrees of freedom were correct. To verify the inverse kinematics calculations, the equation of the mechanism's kinematics model were used as presented here in this slide. The results of the equations were obtained in MATLAB and are present in this table. So the results obtained using ChatGPT are shown in table 4. And we can see the values obtained with MATLAB are similar to those obtained with ChatGPT. So here we have the conclusions. So LLMs are valuable tools to help users perform kinematics analysis mechanisms. They can recommend the steps to follow and the possible applications and uses of different mechanisms. Even though LLMs can recognize kinematics diagrams of mechanisms, the users must be familiar with the field, as they may need to guide the LLM to resolve any ambiguities it detects. To reduce potential ambiguities, it is recommended to provide all information about the mechanisms, both graphically and numerically, so the LLM can interpret and reduce the risk of conceptual errors. As future work, we distinguish the following task. It is suggested to evaluate other LLMs for analyzing mechanisms, such as those for the new to image generation like DeepSeek, and to explore their interpretations of kinematics diagrams. On the other hand, it is recommended to evaluate LLMs for performing kinematics analysis of three-dimensional mechanisms, as these require a spatial interpretation of different rigid body. It is also suggested to explore whether the LLMs can generate code to create CAD models of different rigid body and export them to CAD programs to generate assemblies and other simulations such as finite element analysis. So thank you very much. If there are some questions, I'll be glad to answer them.
Thank you for your presentation, sir. Dr. Galilea, I'm very sorry, Dr. Galilea, do you have any questions?
Another question, kind of the comment here. Really interesting work, especially using the concepts of the artificial intelligence, LLMs and everything into it. My question was, you did mention in the abstract that there is the survey. So what was some of the results of the survey that we could use for the future development of the similar type of the research or implications?
Okay, yes, the survey was applied to students to know the perception about the course. Because they are mechanical engineers, they thought it was interesting to use AI to solve the problems.
Yeah, no, that's amazing because I do experiments similar with my students. I allow them to use the AI tools to comprehend the answers and then try to compare the original one. So just was wondering how does it work in your field. So thank you so much for your work. Appreciate it.
You're very welcome.
Dr. Deore, do you have any questions for our speaker?
No question, sir. Very good work.
Thank you.
Well, thank you so much for your presentation, sir. And that brings us to the end of our session. I now request our session chair, Dr. Josep Gabelea, to give us his closing remarks.
Yes. First of all, thank you so much to everyone for participating and sharing your research findings. It's always interesting to see cross disciplines and see how different type of the research concepts work. So very informative, very let's say I would say not informative just because what we hear. It's also informative because we can learn something from it and then develop our future works not only in one field but in another field as well. So everyone, good job and looking forward to see more of your works in the future. So and then thank you so much for your time and the participation.
Thank you so much, sir. I request our session chair, Dr. Shailesh Shivaji Deore, for his closing remarks.
Thank you so much for this wonderful opportunity given me, and best of luck for all researchers to continue such a type of research and future work. Thank you so much.
Thank you, sir. Well, I now sincerely thank all our authors for their excellent presentation and contribution towards this session, and also all of our participants for being a part of this international conference. I hope this session was informative enough, and on behalf of the entire team of ICICT, we thank you for your support during this 11th version of ICICT, and we will be more than happy to have all of you once again for the 12th version in 2027. A small announcement for all the presenters. You will be getting your digital certificates via email within 2 working days, and the publications will be live within 7 to 8 months. So kindly cooperate with the team of ICICT. I also thank both our session chairs for chairing this session. This is just a small token of appreciation on behalf of Team ICICT. Thank you so much for your valuable presence. I now request all the members in this technical session to switch on your cameras for a quick snapshot of this virtual conference. Yes, we are done. Thank you so much, everyone. Thanks for joining. Stay safe and take care.
Thank you, you too. Bye-bye.
Thank you.
Thank you.
Bye-bye.